section 3.5, base excitation. Up until now, we've always added energy to a system like this from the side, right? Or maybe from this side. And now, what if we have a system where we have excitation coming up from the bottom, right? Particularly if we have a fixity and we have some sort of force. Instead of a force, right, maybe we have a base that's moving up and down, right? So it's slightly different than just applying a force to the mass. We're applying a force on the other side of the spring and the other side of the damper. So this is called base excitation, and this is common for something like a machine on a rubber mount, automobiles excited by the road, hospital equipment. If you look on any piece of hospital equipment, it will have shock and load vibrations on it. Here, like at your home, you might just hang something up on a wall. At a hospital, that would cost hundreds of dollars because everything is certified to survive an earthquake, right? Hospitals are built to a much higher standard because if you have an earthquake, the hospital is the thing that you want to be, the hospital and the flight air traffic control tower, right? Those are the things that you want to be functioning through an earthquake. So in all of our engineering systems, there's a lot more that goes into designing things for base excitations. Earthquakes are a really good example. So let's go ahead and we're going to draw our system. Our first problem here is to do a free body diagram. All right. Oh, wait. So that would be how we would draw it if we had a fixity. And let's draw it with a base. Now, just like before, this is stiffness and this is damping. And I'm going to say positive is up in the x direction. But at the same time now, I have a direction of my base, which is y. So I'm going to be acting on my system at my base. Now, I have an equilibrium position for this. And if I have a mass, I'm going to move this down a bit. If I have a mass, I have a force acting down, which is my mass times gravity, correct? And I also have a force acting up, which is my stiffness times my displacement from the gravitational force, right? So I build the system, I let go of the mass, it's going to compress just a little bit based on the mass of the system. The spring's going to compress, and then I've got a force acting up, and they'll come to an equilibrium, right? Now, if I have a displaced position, let me see if I can. There we go. A bit better. If I have a displaced position, I have a mass. This mass has a lot more forces on it, so I'm going to draw it more horizontally, but it's still the same mass. Okay, I'm going to pull this mass up just a little bit in the x direction, right? X is positive. I'm going to grab the mass and I'm going to pull it up just a little bit. Not enough to counteract what I had before in my displacement. So I still have a k delta, right? But if I'm pulling it up, I'm going to have a force acting down, which is k of x minus y. Why do I have the y there? Because I'm stretching the spring, but if my base were to come up just a little bit, then the total displacement of the spring would be a bit less, right? So it's whatever x moves minus whatever y moves. I have a force acting down, which is mass times gravity. And then I also have a damper. So I have C minus x times x dot minus y dot. There's my nice long mass. So those are the four forces that are acting on my system. All right, so we can build out an equilibrium. We know from solving these a lot that a lot of this is going to cancel out, right? That's why we have an equilibrium in a displaced position. We just kind of intrinsically know already that my mass and gravity aren't going to affect this. I'm going to end up with a basic equation of motion, just like every other time. So let's take the sum of forces is equal to K delta minus mg is equal to 0. So that's for my equilibrium position. And then for my displaced position, I have, oh, I apologize. I'm missing my summation symbol here. Move that a bit to the left. For my displaced position, I have positive in the up. The sum of forces acting in the x direction is equal to K delta moving up minus K times x minus y minus mg minus c of x dot minus y dot. So I know that this system, right? I'm looking for a free body diagram. So I'm just looking for sum of forces equals 0 and Newton's second law. And I can apply from this side, I can apply K delta minus mg is equal to 0. I can apply that into here. And a little bit of rearranging, I get mx double dot plus cx dot plus kx. All looks good so far. Everything else is going to go on the right-hand side. I've got cy dot plus ky. Now, again, this is my, the whole thing is my equation of motion, but the left-hand side describes my system, and my right-hand side describes my forcing, right? Before we had a forcing function there, and now we just have a system there, and that's a y dot.
There's cx dot plus kx. Mx double dot plus cx dot plus kx.
Yeah, plus kx. Yeah.
Sure.
Okay. So we need, yeah.
Why is it ky dot and not just ky?
You're right. Sorry, it is ky. Correct. Okay. We need a function for y that we can use to excite our system. So every time before, we've just chosen an arbitrary trigonomic function, and we're going to keep doing that. Sine and cosine are the most obvious answer. We say sine first, so let's just pick sine. You could pick cosine and get the exact same answers. So I'm going to say that y of t is equal to capital Y of sine omega b of t. What is omega b? That is the frequency that we are exciting the base at, right? So we've had omega for the frequency we're exciting from the side. We've had omega n for the natural frequency of the system. We've had omega d for the damped frequency of the system. And omega b is the frequency that we're going to excite the base at. So I can rewrite this whole thing out now as mx double dot plus cx dot plus kx equals c capital Y omega b cosine of omega bt plus k capital Y sine of omega bt. And the capital Y is the scalar for the amplitude of the forcing function. And again, we get cosine by taking the derivative of sine. That's what happened to our y dot. This is a, you don't write much down, write this down. That is the equation of motion for a base excited system, 1 degree of freedom with stiffness and damping. Okay. We can get that in standard form if we divide by whatever leads the x double dot term. In our case here, it's just mass, and apply the equation for critical damping. We can get x double dot plus 2 zeta omega n x dot plus omega n squared x equals 2 zeta omega n omega b capital Y cosine of omega b t plus omega n squared capital Y sine of omega b t. So another way that this can be written is written quite often is that these terms here, let's do this in red and blue, can also just be taken as arbitrary values. And you can get the exact same term if you just want an arbitrary input, right? So if you're just exciting the system to figure out how it responds mathematically, the details on the right-hand side don't actually matter a whole lot. So you can rewrite this as x double dot plus 2 zeta omega n x dot plus omega n squared x equals to c cosine omega bt plus d sine of omega bt. And c and d can be arbitrary coefficients because often you're just looking to see how a system responds in the frequency domain for a base excitation.